So, hello everyone, welcome to my seminar on multi-AUV mission planning and execution under the sea. My name is Özkahraman, and since I am getting close to the end of my PhD, I would like to show you a wide overview of what I have done and how they all connect together. Coming to the end. So I will, oh, where is this? So I will start with the big picture. You know the project. I will go through how its goals and its parts connect to what I have done. And then I will go through the papers that I have published or somehow sent over. And then I will talk a bit about what I want to do in the future. And I will be kind of quick with all of this because you already know most of these. As you remember, we have environmental sensing, ocean protection, and safeguarding society as the three main goals of SMaRC. And these all have some stuff in common and some stuff that are not in common. For example, coverage is one of the most common missions that we want to do for all three of these goals in SMaRC. Caging and capture is a very specific one for mostly safety, and safe and parallel execution is also a common theme amongst all of these. We define coverage as sensing of an area in its entirety without any gaps and such. And it basically gets better with more agents. The more agents you have, the more area you can cover, and the less error individual agents will have to accumulate, meaning your maps or whatever you're producing out of your coverage is more accurate. We want guarantees and optimization at the same time in the coverage scenario. Also, I keep dropping onto the thing with my finger. Caging and capture can only be done with multiple agents. You cannot do a cage with one agent. As you can imagine, if you have a bunch of things that you want to cage, I have a lot. Very fine. And it requires coordination and placement of multiples of these agents. And the placement is dependent on very particular things, like do you have maps of the area? How many agents do you have? How fast are your agents, and so on and so forth. It's mostly an optimization problem, mostly because we usually require a lot of agents to do this mission. And we would rather not have 120 agents to do this caging operation. We would rather reduce it as much as we can while still completing the task. Safe and parallel execution is, I think, obvious for most of us. We want to keep whatever robot we're using safe. We want to have multiple agents, which compounds this safety problem multiple times, because now you also have to think about other agents crashing into you, not just you crashing into a rock. And their interactions make things even more important, because for them to interact, they need to come closer, meaning they put themselves at physical risk. When all of the agents are scattered around, you don't have a multi-agent system, you just have multiple single-agent systems. And in this case, we want guarantees. We want to make sure that they never crash into each other and so on. So going back to why use many agents when few of them work. From Wikipedia, oceans are about 361.9 million square kilometers, and an even more ridiculous number, cubic kilometers of water. That's a lot of water. If you do some back of the napkin estimation with some very optimistic numbers for what our AUVs can do, a large AUV can go from 500 to 1,000 kilometers, very optimistic. Side scan multi-beam SWATs are around 220 to 200 meters. So we can cover 10 to 200 square kilometers per mission, supremely optimistic. And if you want to cover everything, that's 1.8 million missions. You can see why it's a little ridiculous to attempt this with one vehicle. We need to have fleets of agents going everywhere all the time, continuously, autonomously, so we can actually get there. And some missions, as I said, like caging, is just straight up impossible with just one agent, and we have multiples. And these are the vehicles that I think we, if not all, most of us are familiar with: Sam and Lolo, small and big, and then there's a wild hugin in the background. You can ignore that one for now. So what is available? Like, what can we use today? What can we just read a paper about, implement it, and get working? I will use some symbols on the top right. These are related to the four main things that are required for a multi-agent mission from my perspective. We have planning. If you have a plan, you can reduce your communication requirements, because plan is basically communicated beforehand. We have communication. If you're coming close, most of these agents do not have 360 vision. They need to communicate where they think they are so they can avoid crashing each other. They need to update their plans live and so on. Control, I think, is obvious. We need to control these things to go from point A to point B in the states that we want. And navigation and sensing, I'm putting into one. It's mostly SLAM, meaning we want to know where we are, where the map is, and what is in the map all together, combined with the sensing equipment that we actually have. Side scans and multi-beams are basically lines that we can use as a brush to scan the ocean floor, but they all have their idiosyncrasies, like you don't want to tilt your vehicle while you're scanning, otherwise your densities are going to be changed different on different sides, and so on and so forth. There's a bunch of papers. They all attempt different parts of a multi-agent system. You have the planning papers, you have the communication papers that try to either create, for example, Jose Pinto, as you can see from LSTS, is one of the most important things in this communication part. And then we have the control people trying to do different things like non-smooth barrier functions, and that barrier functions are the most useful so far. On the sensing side, we have a lot of SLAM papers that we can just plug in. And then there are like combinations of these things as well. As you can see, I'm not going to go through all of them one by one. There are very few that take 3 of these fields into account at the same time. I have yet to see one that takes all 4 at the same time, unless it's a demo paper, basically. Even then, I think we all agree that there's a lot of things that go on in demos that are not exactly what we wanted to do, but what we had to do at the time. So even then, those papers I'm not going to consider as complete work. And the question is, how do we get a paper or a result that is all 4 at the same time, all the time, and in a complete manner without any hacks and tricks? And that's what I have been trying to get to with the 6 papers that I have, and some of you are in those papers as well. Starting with caging. This is the one mission that is specific to multi-agent systems. You cannot do this with one agent because, as you can see, you need a bunch. I'm not going to play the video for now because we don't have the time for it, but you can watch it in your own time. We have a lot of agents that need to cage one vehicle, and in 3D that looks like this. These green cones, you can imagine them as forward-looking sonar sensor slots looking forward, and the balls are the agents, and the red area is where the caged submarine could stay without being captured. In this case, capture we mean as seeing the caged agent in its entirety. You can do this with the aid of the bathymetry, if you know the bathymetry. If we look at it from a safety standpoint, you should know the bathymetry of your own waters. So it's an acceptable assumption to know this. And this can help us reduce the number of agents we need. Because in 3D, you need a ridiculous number. In 2D, we can actually use islands and the shallow parts of the water to have few agents and use the islands and shallow areas to our advantage to create a cage. I have shown this before. I think you probably all remember. And then we get to the planning and control side. That was the entire planning. Behavior trees, as many of you might have heard before me and from Chris as well, are very useful because they can give us the safety, emergency, calibration, finalization, all of these individual elements of a mission in a nice chunk. We can test it individually, and then we can trust that part until we change it again. And then we can keep adding. It's this modular structure that allows us to write once and keep using the same thing over and over again. This we have been doing with SAM and Lolo since 4 years ago, basically. Since we wrote this paper, we have a behavior tree on SAM and Lolo. It's been running, and I don't think I have touched the safety part since then. Like, it's still running and it's still fine because it is done. But we have been having fun with the other parts of the tree without touching the safety part. We know it works. We know it will keep it safe. It's good. So we can play around with the other parts without thinking about the safety of the vehicle. And that has been useful. Again, planning on control side, I have written a paper about control barrier functions and behavior trees put together. Control barrier functions are very useful because they give you continuous control, continuous constraints and requirements, but they are not very good at switching between priorities. And that's what the behavior trees do best. They switch between priorities, no problem, that's what they're made for, but they can't do continuous stuff until you specifically put an action that basically invalidates the behavior tree and then just does the continuous part. And that's where the merger makes the most sense. Here's an example, for example, just with the control barrier function that are multiple of them combined, these blue balls are the obstacles and the light area is like a safety distance that we would like to keep, but it is not entirely critical. Like, we can go inside, no problem, but we would rather not. A control barrier function will give you this nice control. It will go all around all of the obstacles, no problem, but it doesn't know that it cannot reach the point while following all of the constraints. On the other hand, the behavior tree can get stuck entirely because it will go in, out, in, out. If it's naively designed, it will start chattering and then never finish the mission either. When we combine them, we can get the nice smooth control of the control barrier function until a point where the behavior tree can then switch to a different behavior saying, oh, we are going to run out of fuel. Stop caring about the safety distance. We can now take a bit more risk to complete the mission. It is now worth it. And that's what the behavior tree gives us, the switching behavior of different constraints whenever we need it. And you can also apply this to multiple agents, which was the whole point. Here are the constraints and goals of these three agents you see on the right. Avoid collisions with each other and the place around them. Have enough charge to reach base, so always be able to recharge. Stay within communication range of each other, so you're not alone, basically. And go through all the waypoints that you have. And these are the three agents. The circles around them show their communication range just by themselves. These are the obstacles, the blue blobs. And then you can see this pink one starts with less fuel than the others, just to make it interesting. They start, the pink one runs out of fuel and goes back. Because fuel is a higher priority than staying within range, it gives up on staying within range. The other two have all of their priorities or constraints fulfilled. They continue their mission. Eventually it fills up after going back, and then starts to have rendezvous, because now being within range is a priority again. But at that point, since these two have been running around for a while, now they run out of charge, and the pink one is the only one that has any charge left. So it is the only one that's trying to keep the connectivity constraints still fulfilled in this order of priority. And once these two are charged back, they can just finish, and then at some point the pink one runs out of fuel again, goes back, recharges, and finishes the mission. And as you can see, we can just keep repeating this whole mission basically infinitely. And these constraints in this priority order will always be fulfilled because of control barrier functions merge with behavior trees. Going forward. So that's a lot of theory, lots of simulation. We also did a lot of integration. Some of you will probably remember this beautiful picture and those pictures on the right. I think Harsha is in this paper. Yes, definitely you are. I think you wrote it mostly. But integration, we had to put things together on a real vehicle, and that's what we did. We have this ridiculously large behavior tree, which doesn't show all the details in it. It's just a summary of it. And then we have a bunch of pieces. We have the behavior tree that is doing the mission control side. We have the motion planner trying to find out like what curves do we need to follow. We have the dead reckoning trying to understand where the vehicle is at all times. And we have the controller that is actually controlling the vehicle. And all of these need to work at the same time. And we also have this fun idea of we want the hardware, the stonefish simulator, and the Simulink simulator to be entirely interchangeable. We want to be able to unplug this, plug this in, and then not touch this side of the whole thing. That's actually works just fine nowadays when the hardware is there. And of course, we also had the operator side, but that is not very important. Therefore, we integrated all the things. And they work just fine. And then we tested it. We took one of these, put it in there in Christineberry. I think that was a lot of fun. Oh, this was an Oscar. That's what the vehicle did, completely autonomously. We found the car. You can see the car in the water, and that's what it looks like from the top. We just did like a simple spiral mission. At some point, you can see this jump in the trajectory. I believe that is when it went to the emergency mode and actually surfaced, got a GPS fix, and actually reset its inaccuracy in the SLAM system, and then continued on from that. You can see the behavior is keeping things safe. And that's the car there. It's a picture. There's Ivan with the keys, the Mini, and it was MMT's Mini, and the whole thing was thanks to them. And it was a successful mission. They actually ran the whole thing with no problems, actually. Cool. And that was a three-way paper. If you see the symbols, it doesn't have the communication part still. Then the question arose is from that is, okay, we do all of these, like we did the spiral pattern. Why did we do a spiral? Why did we not do a lawnmower, or why did we not do a flower like in and out from the center shape? What is the difference between these? How efficient are these? What is the problem? Like, how can we make these? How can we make the search? How can we know these patterns are good or bad? These are the most common coverage patterns, and the problem is usually what you get on the right. The vehicle tries to cover a rectangular area in the case of a lawnmower pattern, and it drifts. It will drift. This is unavoidable. Meaning you will have a bunch of uncovered area, and if you don't know about this drift, you think you covered it. If you're looking for mines and you missed a mine here, you don't know about the missed mine. This is a big risk. Now people can die because of this. We don't want this to happen. We want to have guaranteed coverage in the place that we say we have guaranteed coverage, even when you drift. And AUVs are expensive, as most of you know. Thus, we need efficiency. We need to be able to use these things as efficiently as possible. When you put it in water, it takes 3, 4, 5 people there standing around trying to fix things, running the boat, and so on. It's a very expensive operation to use an AUV nowadays. So whatever we use it for, it needs to be done proper and done quick. So can we adapt these patterns into account to take into account this drifting that will happen? The answer seems to be yes. Basically, we did the math, bunch of math. You can see the paper for the details. You can forget about the math. I'm not going to go through it. And we can take them into account. For example, in the lawnmower case, we can make it larger and larger as you accumulate inaccuracy, or drift and inaccuracy I'm going to be using interchangeably because it causes the same results. Make your pattern bigger, make your pattern tighter as you go on, as you accumulate, so you never, even if you're inaccurate, you at least know that the middle is covered. But there's a limit. The more tighter you make, the wider you make, the more ridiculous it gets, and there's a limit at which point tightness means going backwards, which is not exactly a good thing. But it's a calculable limit, and we wanted to know where the limits are for these different patterns. And here are the limits. Spiral, funnily enough, is the worst one out of all of them, in my opinion. You can see it doesn't really reach a large radius. A spiral covers a circle, so does a flower. It doesn't reach a large radius, but it can get the most efficient out of all three. Mostly because it's in small radiuses. You can see 40 meters, and swath is 50 meters for all of these. It's basically, if you basically turn in place, you move very little, but you cover a very large area. That's what this peak is, which is not exactly useful. Flower is, if you look at the efficiency metric of the flower, it gets less efficient with size. You can go up to 500 meters, and it still stays around 40-ish%. It drops very slowly, which entirely comes from the fact that when you're doing these loops to the same point, you can do loop closures, meaning you can reset your inaccuracy every time you come to the center. So the entire inaccuracy accumulation is coming from one flower shape, going out and in, and then you reset it once you see whatever you have in the middle. Thus, it reduces inefficiencies a lot slower than everything else. And the lawnmower has two parameters that you can play with, the size and the height, basically. X is to the side, meaning how long your lines are, and Y is how many lines you have. And you can see this like stepping function that is changing angle as it goes on. You can imagine why. If you have a lawnmower and the top side, if you're doing this, because forget the last one, if you're just doing this, this is inefficient. You're doing a lot of coverage you don't care about. You're just doing this just to cover this like one tiny bit that this one didn't cover. Hence the step. As this goes up, it fills in this, gets to a maximum, and then steps down when you do another line, just because you have to cover a very tiny part. And when we compare them together, of course, in a log area scale, in this case, the lawnmower is doing a square, not a rectangle, just to keep things simple. You can see that the lawnmower, if you can get to the peaks, it's the best, but the peaks also go down as you increase the area that you want to cover, obviously. But the flower is not as efficient as the rectangle, the lawnmower pattern, but it can get significantly larger at lower efficiencies. So there's a trade-off. If you can get to the peaks, if you can stay on the peaks, use a lawnmower basically. If you need really large areas, flower is your only option. And these tiny bits here are the spiral, telling you forget about spiral. Spiral is the worst, which was an unexpected result to me, because spiral looks very efficient, but when you consider if you're turning, suddenly your inside and outside are different densities. It gets even worse. We didn't take that into account here. And this is what they look like when drifting or inaccuracy happens. These three are when there is no inaccuracy at all. It's following the plan perfectly. We can see the coverage, the blue areas, and the darker it is, the more overlap there is. Spiral, the overlap gets larger and larger. And you can see the ridiculous amounts of overlap in the flower. That's why it's 40%-ish efficient a lot of the time. This central overlap cannot be gotten rid of, unfortunately. And when there is a drift, we guarantee that this rectangle is always covered. You can see that there's a drift to this side and there's a drift to that side. It's still covered. There's still no gap in between, same in spiral and circular flower. In the worst case for drift is like right there, following this vector basically. No problem. That's how we calculate the circular area that it can cover. So this gives you guarantees. You do more work. Yes, the efficiency is less compared to assuming you have no drift, but this gets you a guarantee that that rectangle is covered. There's nothing you missed in there, whatever the case. The only assumption is you know your maximum amount of drift per meter. This you can measure before. The main takeaways I just said. And then the question is, what if we have multiples? As you can imagine, SLAM handles drift, trade-off between navigation and efficiency, I just told you. And what if you have no features, meaning you cannot do the flower? There's nothing, it's sand, it's a desert, you're looking for something maybe. You can get multiple agents, one of them can do this, multiple of them will probably do this if they don't communicate. If you get them to communicate when they meet, because the lawnmower pattern, when you mirror it, get to these natural meeting points when two of them basically do this. At that meeting point, you can actually communicate your measurements, you can communicate your, you can measure each other's locations, and that gets you a loop closure in graph SLAM. And that is ridiculously useful. This is how it looks like. You can communicate, you split apart, you meet with this guy, measure that guy, you go around together a bit, you keep measuring the guy, you forget about him, you see him again, suddenly you have a loop from here, you have measured him before, he has his own thing, he sends you this part, you have measured him here as well, and then you suddenly have this loop. And this loop closure helps with the inaccuracy of SLAM immensely. It usually reduces whatever inaccuracy you had to like 20 to 30% of its original, which helps you do a lot more in the same amount of area. Then the question is, how much data do we need to communicate? Because communication underwater, as you know, is horrible. Surprisingly, not much if you compress your data properly, which is what I have in the paper. You don't need to send the entire pose graph. You can summarize it. And once you do summarize, from 340 kilobytes of data, you need 8 kilobits per second to transfer that. The formulation is in the paper. You can see the calculation there. Yeah, you can go down to bits per seconds if you summarize the graph enough. And this is what the efficiencies look like. If you don't do the communication, if you do the communication, red and black, red and blue, you can see the difference in both coverage percentage that you have done for different line distances and different numbers of lines. Either way, communicating and doing all of this is just 8 to 10% total coverage better. And this is how it breaks, by the way. If you go to some ridiculous extremes, 4,000 meters, 4 kilometers in one direction, they can, if they miss a meeting, they can diverge. And this is what I'm working for as we speak, making sure that that doesn't happen. As I said, elephant in the room is, can we guarantee rendezvous? That's what I'm working on. Yes, we can. It's kind of harder, but we can. It will cost efficiency, but if we can get the total coverage to an extreme, that we can. And we also need more autonomy. Things break on the fields. Great example, like we didn't have a magnet when we needed a magnet, so we had to use a magnet on the boats by putting SAM in interesting positions. These things happen, and these things also happen underwater. You get the seaweed on your propeller. What do you do now? Can you detect this? How can you detect this? How can you get rid of that propeller seaweed autonomously? That's what I want to work on eventually. So when you put all the things I have done together, you actually do get a 4 symbol results. If I can squeeze them together, I just need to test it on hardware eventually. And the limit is the Mariana Trench at that point once I'm done. Hopefully, not the sky. You go down. Thank you. That's it.